Thanks to Henri. I'd like to publicly thank him for all his efforts in the Gen 4 Secretariat, without whom my job would be impossible. So I'm going to talk a bit about looking ahead. Henri touched on it at the end of his presentation on Generation 4 systems. Okay, this sounds like the next product from the nuclear industry, which is going to solve all the problems. I can assure you it's not. Some of these technologies go back to the actual dawn of nuclear power, particularly things like sodium-cooled fast reactors. So without further ado, just the scope of the talk will be looking at some facts around natural uranium. We'll look at plutonium breeding, the motivation for actually recycling spent fuel. We'll look at a technology called fast reactors and how that kind of changes the game and the timescale of how long we can expect nuclear energy to last. Transmutation of minor actinides I will talk about, and I'll explain what minor actinides are, so don't worry about that. And then just a very quick run through some of the more promising fast reactor technologies which have actually found place in the Generation 4 program, and then to finish off with some conclusions. So I listened with interest to the earlier talks. I don't believe there is a powerful nuclear lobby. I believe that I kind of represent probably a bunch of very keen enthusiasts who can see the long-term potential of nuclear energy. And so there are few of us, but we try to be as vocal as we can. So anyway, look at natural uranium. Natural uranium occurs with both what are known as fissile and fertile isotopes. And a fissile isotope can undergo fission easily in the world's power reactors. So we can split it and we can reduce energy. We can produce energy. A fertile isotope does not fission readily in a thermal reactor, but some of it is converted into fissile isotopes in a reactor. The way to actually look at this is you've got a big pile of firewood, and 99.3% of that firewood is wet, and only 0.7% of it is dry. So we can only actually use 0.7 of it to start a fire. But then once we've got that fire going, we can use that fire to dry out the other 99.3% if we wish to. So at the moment, we're only working with reactors which are capable of using this 0.72% of natural uranium. If we look at the global reserves of uranium, the known reserves at the moment are 7 million tons. The speculative reserves are 10.4 million tons, and this came from the 2011 OECD NEA joint IEA Red Book, as it is actually known. That's not its official reference, but everybody knows it as the Red Book. So these are reasonably recent figures. If we look at the current consumption, and I think Henri touched on this, we are consuming 64,000 tons a year for a current fleet size of 375 gigawatts electrical. And by 2035, the fleet size is expected post-Fukushima to grow to a 540 to 746 gigawatt fleet. So again, we'll need about a third more uranium per year as the minimum by 2035, even after taking into account the Fukushima event. So, World Nuclear News back in the middle of last year published this article saying uranium supply is okay for the long haul. And I think Henri's mentioned this, that really the long haul in the World Nuclear Association's perspective is 100 years. Is this really the long haul when we look at the time constant for things like accumulation of CO2 in the atmosphere and just the time constant of the human population, I guess? If we've got nuclear energy for 100 years, what do we do after 100 years? So thankfully, there is a thing called the plutonium breeding reaction, which enables us to use the other 99.3% of the natural resource which is available. It's still not a huge natural resource, but it'd be quite nice to use more than 1% of it. So we start off, once we put natural uranium into a reactor, the bulk of which is uranium-238, that captures neutrons and it becomes uranium-239. That uranium-239 through radioactive decay in about 23 minutes decays into neptunium. That neptunium, 2.3 days later on average, decays into plutonium. And that plutonium itself, plutonium-239, is not the most radiotoxic element on the planet, as most people would have you believe, by a couple of orders of magnitude. But that plutonium-239 is actually an excellent reactor fuel, an excellent fissile material. We can also do an analogous reaction with thorium. And thorium is an interesting material in that it's actually more widely distributed throughout the Earth's crust than uranium is, and there's quite a bit more of it. There's about twice as much thorium in the crust than there is uranium. The problem with thorium is there isn't a fissile isotope. So we can only start a thorium breeding reaction if we started off with uranium or plutonium in the first place. But I think it's got great potential for the future. So if we look at what form the fuel actually takes in the reactor, and this is a typical pressurized water reactor element, and this is probably the mainstay of 95% of the power reactors in the world today. This is a Mitsubishi element, but it's only a Mitsubishi element because that's the only image I could find with a reference to the manufacturer. So basically we have a bundle of fuel rods which contain slightly enriched uranium. And slightly enriched uranium is basically uranium in which we've artificially enhanced the uranium-235 isotope. So if we look at when we put new fuel into the reactor, each element contains about half a ton of natural uranium. About 4% of that will be the actual useful uranium-235 isotope. So out of the 500 kilograms of uranium in there, we've got 20 kilograms of actually usable fissile material. Once we've irradiated that in the reactor, typically for about 2 to 3 years, we'll end up with 20 kilograms of fission products. Fission products are what we get when we split a heavy atom in two, basically. The mid-periodic table elements, highly radioactive, and no further use for power production, but they could be used for medicine and things like that. At the moment, they're just waste, and they go straight into high-level waste storage. We also get 475 kilograms of uranium back, which effectively hasn't been consumed or converted. And of that 475%, 0.9% of that is uranium-235. So the uranium we get back from a spent fuel element, if we reprocessed it, is actually more highly enriched than what we dig out of the ground in the first place. And at the moment, without recycling, that also goes to waste as well. So we can recycle that immediately we just send it back, re-enrich it, and put it back into the power station. I apologize for the Simpsons-looking power station, but it was the only non-copyrighted image I could find. And the icing on the cake is we also get 5 kilograms of plutonium produced, which, as I said before, is a very good fissile material. That can also be used, recycled in a power station. So in total, we can recycle 480 kilograms of that 500 kilograms of original material that we put into the fuel. So we only, in reality, have to dispose of 20 kilograms of it, not 500 kilograms of it. And of the material we recycle, we get 9.3 kilograms of fissile material back, which is almost half of the original fissile content of the fuel. So that's the motivation behind recycling. Like all recycling, it's to conserve the initial resource, and also it's to reduce the amount of waste that we need to send to geological disposal. The other thing we get in nuclear waste, besides fission products, are things called minor actinides, or transuranic elements, very heavy elements, heavier than uranium. And effectively, the plutonium breeding reaction I showed earlier is a bit more complicated than that. It doesn't stop with plutonium. The plutonium itself can absorb neutrons and then become heavier elements like americium and curium. The neptunium, when it's decaying, can absorb neutrons and become higher isotopes of neptunium. These elements are very radioactive and have very long half-lives, tens of thousands of years typically. So when we talk about disposing of waste and putting it at a geological time, into a geological disposal for sort of geological timescales, it's because of the presence of these elements, not the fission products. At the moment, we don't separate, even in commercial reprocessing, we do not separate the minor actinides from the fission products. So the waste we send into storage has half-lives of typically 20 to 30,000 years. So this bunch of problematic elements is the ones which give rise to very long storage times in the waste repository. So, I'm going to talk a bit about closing the fuel cycle. I'll come back to minor actinides later and the advantage of actually removing them and reusing them. So a fuel cycle typically starts with a uranium mine. We then do some chemistry to process the ore and some milling to get it into a more manageable state. We then enrich it to increase the uranium-235 content. We fabricate it into fuel. We irradiate the fuel in the reactor. Then we can take that spent fuel, break it down, recover the elements and isotopes that we wish to recover, and then dispose of the fission products which we can't reuse, and then recycle it around the whole thing. Ultimately, we can do away with the mines altogether, because we've got enough fissile material going around the circuit and enough uranium-238, which we've previously have previously extracted as the tails of the enrichment process, so we can actually put new fuel together without actually having to dig anything out of the ground. So this is a very wordy slide. I'll not spend too much time on it, but basically all reactors which contain uranium-238 will breed plutonium. There's a measure of the efficiency of that, which is called the conversion ratio. And all the world's power reactors today, PWRs and BWRs, have got a conversion ratio of less than 1. If we recycle the fuel around the reactor, we get that series, NT equals N plus CN plus CN, C squared N, and so on, where N is the number of fissile atoms we start with, and NT is the number that we would end up with, or have ended up with, if we recycled a certain number of times. For C is less than 1, that series actually converges, and it converges to a finite value. So for a light water reactor with C equals 0.5, typically, the absolute number of fissile atoms we end up with was twice the number we started with. So the conclusion was the large-scale recycling light water reactors alone results in very limited conservation of uranium. We can double the uranium supply, but not more than that. In practice, the plutonium vector degrades. We get heavier and heavier plutoniums, which are less and less able to be fissioned in a light water reactor. So in practice, we can only recycle once in a thermal reactor, a typical power reactor. So in reality, we only increase our number of fissile atoms by about 50%. So instead of having 100 years of uranium, we get 150 years of uranium, which is still not good enough. Fortunately, we have another type of reactor called a fast reactor, and that makes use of fission induced by high-energy neutrons rather than low-energy neutrons as in a conventional power reactor. So it has a high power density core, and both breeding and the utilization of plutonium are more efficient in a fast reactor. And we can set the fast reactor up so we can have it as a net destroyer of plutonium, so it can have a conversion ratio from 0 pretty much all the way up to a practical maximum of about 1.6, so we can get 60% more plutonium out or fissile material out than we actually put in the reactor to start with. So also these long-lived minor actinides in the nuclear waste, americium, neptunium, curium, can also be burned. So if we look at the same recycle scenario with a fast reactor fleet, we can theoretically increase the amount of fissile material we have up by a factor of 100. So if we have 100 years worth of uranium now and we increase it by 100, that's 10,000 years worth. So in reality, there's a few losses, so we might have to temper our expectations to be about 4,000 years instead. But anyway, that series tends to infinity if we put in a value of C greater than 1 for a fast reactor. And we can't get infinity because we don't have enough feedstock. The uranium-238 will run out before we reach infinity, but we still have enough for about 4,000 years as a fairly conservative estimate. And we've probably got as much or more again if we do the same thing with thorium. So other than maybe some of the renewable technologies, and even they are bound by resource limitations, we're looking at an energy source which has the potential to last for millennia. The other advantage is the plutonium vector does not degrade in fast reactors, so it can recycle indefinitely. We reach an equilibrium, and the fast reactor can still burn it. And so the only limitation is feedstock. This was a graphic produced by the Generation 4 International Forum back in 2002 with the forecast demand for nuclear power as it was then, plotted against the amount of uranium we knew existed at the time. Interestingly, the known reserves have increased quite a bit, but the known plus speculative is still pretty much the same at 17 million tons. So the only thing which has changed post-Fukushima is that light water reactor once-through curve is now a bit shallower because of nations backing away from nuclear power. But the principle is still the same, that we have, if the world continues with light water reactors once through, then we will start to run out of uranium probably towards the end of the century. The other problem we have is we start to accumulate more and more spent light water reactor fuel, which is quite bulky, as we saw before. All half a ton of material needs to be disposed of rather than just 20 kilograms. So we have an ever-increasing stockpile of spent fuel as well if we don't have fast reactors. The impact on the back end of the fuel cycle is even more impressive. The fact that if we do nothing, if we just dispose of spent fuel, we have to wait for that fuel to decay by about 10 half-lives, which gives us about a 300,000 year storage time. So our geological disposal facility has to be documented and has to be stable, and people have to know about it for 300,000 years. If we take out the plutonium, as we currently do in the UK and as they do in France, then we reduce that storage time down to 30,000 years, which is still a considerable undertaking to assume that humanity will still be aware of the existence of this material in 30,000 years' time. If we take out the minor actinides as well and burn them in a fast reactor, then that storage time reduces to 300 years. So we've reduced the storage time by a factor of 1,000 by recycling those materials through a fast reactor. And 300 years for storing and documenting something is feasible, and it's done all the time in parish records and cathedrals and things like that. So we know that's achievable. So moving on to generation 4. Generation 4 was kicked off in the early 2000s to look at what came next after the light water reactor fleet, which the world is using at the moment. And it was initially those nations represented by those flags got together to debate which of the most promising technologies should be investigated, and 6 systems were proposed. 3 of which were initially fast reactors: the sodium-cooled fast reactor, the lead-cooled fast reactor, and the gas-cooled fast reactor. And of the others, the molten salt reactor has now got a fast spectrum version, and also there's a fast spectrum version of the supercritical water reactor as well. So you could now argue that 5 of the 6 systems were dedicated to breeding. The very high temperature reactor, which is the still surviving thermal reactor in there, that main mission is what Henri touched on, of alternative uses for nuclear heat. It's a high temperature process heat producing reactor which we can use to synthesize hydrogen and other hydrocarbons, or use for producing glass or for producing metals and things like that. So that's looking at broadening the application of nuclear power beyond electricity. So just a quick run around some of the technologies. The first and well-established one is a sodium-cooled fast reactor. The first reactor to ever export power off the site was EBR-1 in the USA in 1951. I think it lit 250-watt light bulbs in the city of Idaho Falls. So far from this being a Generation 4 technology, it was actually the first reactor technology to ever export electricity off the site. The coolant is liquid metal, liquid sodium, and it's contained in an unpressurized pool system, and the heat from that is extracted through a heat removal system which drives a turbine. That is by far the shortest and most definite route to fast reactor technology, and that is the route that France is actively pursuing today with their Astrid program. France had a go in the 1990s of producing a full-scale plant called Super Phoenix at Crémavis. It had more than its fair share of first-of-a-kind problems, and eventually it was a casualty to political pressure, which was brought by the then coalition government, of which the Green Party controlled quite a fair share of it. So effectively, Super Phoenix was sacrificed on political grounds rather than technical grounds. The UK also had a go. Right on the northern tip of Scotland, we had the prototype fast reactor, which operated successfully for many, many years, and then was closed down in the 1990s, post-Chernobyl, when it looked like the demand for nuclear power was maybe never going to recover. But certainly the UK has had a very strong position, equal to that of France, in sodium-cooled fast reactors. This is a system close to my heart, which is a gas-cooled fast reactor, which I've ran European projects on for about the past 6 years, looking at trying to combine the sustainability aspects of fast reactors with the process heat capabilities of the VHTR. So using a reactor as a high-temperature heat source to do other things than generate electricity. So we can produce process heat, we can produce hydrogen, and so on. And these other forms of electricity are a way of actually getting flexibility. We call it nuclear cogeneration of heat with something else. So we can vary the fraction of heat and electricity depending on the demand conditions at the time. So we can have a very flexible system. Just a technical highlight, I think it might have been David Shropshire mentioned more accident-tolerant fuels. This is one of the spin-offs of GFR technology is the development of silicon carbide cladding technology. This is also gaining popularity in light water reactors following Fukushima because the silicon carbide doesn't have the same strong reaction with water to produce hydrogen that zirconium does. And also, we can take it well beyond 2000 degrees C before it even considers melting. So it's a much more robust accident-tolerant fuel. So this is a spin-off technology. So even if we don't pursue GFR, I think so far the activity has been worthwhile in terms of the spin-off. Lead-cooled fast reactors, these were originally developed by Russia, or lead-bismuth reactors developed by Russia for their submarine fleet, because you get a small, compact, high-energy power source. The idea is to try and take that technology and civilianize it, if you like, to form power-producing reactors. There are a couple of projects going on in the world at the moment. S-Star, which was being developed by a company called Hyperion Power in the States. I think they're now called Gen 4 Energy. There's a small modular reactor of up between 10 and 100 megawatts. Completely passive, no pumps, just uses natural convection to convey the coolant. And within Europe, we've looked at larger prototypes as well. Finally, I want to say a few words about the molten salt reactor, because initially this started off as a thermal reactor. It was a graphite moderated reactor. For want of a better word, the really cool thing about these reactors is the fluid which cools the core and the core are one and the same. It's a liquid fueled reactor. So we don't have to manufacture fuel elements, we don't have to break them down to reprocess them. In fact, because the fuel is a liquid, we can even reprocess it on the same site. So there are a lot of advantages in effectively closing the fuel cycle within the power station, never mind within the country. So the original concept was epithermal, and we've since moved on to the molten salt fast reactor, which basically has a completely closed fuel cycle with on-site reprocessing. Once it reaches its equilibrium condition, once we've started it with something like plutonium, all we've got to do after we get a sustaining reaction is feed it with uranium-238 or thorium-232, and everything else is recycled on the site, and the only thing to leave the site is the fission products. So it's actually quite a neat closed fuel cycle, effectively within a single industrial concept. So if you like, the feedstock for that is the damp firewood, uranium-238, uranium-232. It does all the drying and processing, and all we get, if you like, is ash coming out the back. So the molten salt fast reactor does achieve sustainability. Unfortunately, like most of closed fuel cycles, you kind of have to wait a long time before it becomes sustainable. So you can see around about 100 years, the curves are actually starting to flatten out. This is looking at the concentrations of the various isotopes, uranium, plutonium, neptunium, curium, americium, and so on. The two scenarios there, one if we start from uranium-233, where everything flattens out a bit more quickly, and one if we start from plutonium. Clearly, we can't start with uranium-233 because it doesn't exist naturally in nature, so we have to start with plutonium. But after 100 years, and if we're talking about reactors which are going to be operating for millennia, what goes on in the first 100 years is largely irrelevant anyway. So it's just a very nice demonstration that this really is a sustainable system. We don't get accumulation of anything, we don't get depletion of anything. The only thing we're consuming is the feedstock. The technology is fairly simple. It's just a tank. There's no moderator, so it's just a tank of fissile solution with some heat exchangers and pumps to remove the heat from it. The technology, the concept is simple. The actual making it work in terms of the materials, material compatibility issues, maintenance, things like that with using a highly radioactive liquid are actually quite challenging. And that's where the main challenge lies today, I think. So the conclusions. The case made for the development of fast reactors, made right at the dawn of the nuclear industry in the 1940s and 50s, are still relevant today. The only thing which has changed is there's more uranium in the world than we thought originally, but not a huge amount more. And the deployment of nuclear power has been considerably slower, not least because of the various setbacks that the industry has seen. The majority of systems considered within Generation 4 are fast reactors or now have fast reactor variants. So that's kind of, if you're looking at the Generation 4 type timescales, to a large extent, it's really only the fast spectrum systems make sense in terms of the amount of uranium that's in the world. So without fast reactors, nuclear fission will have a lifespan of only about 100 to 200 years, considerably shorter than the lifespan of coal, for example. With fast reactors, we can generate thousands of years of electricity and other energy forms as well, producing liquid fuels for aviation and all these great things, using a small refinement of effectively, and I think the term was used earlier, what's off-the-shelf technology, 1970s technology. We don't really have to do a huge amount more than what's already being done. The materials and engineering issues with fast reactors are necessarily more complex than for thermal reactors. There's been lots of debate about whether even thermal reactors are too expensive. We accept that fast reactors will be more expensive again. However, there are not many other technologies that can boast a 4,000-year lifespan. So if we can overcome these challenges, and I think probably the challenges today are more financial than technical for any kind of reactor system, we need to find more creative ways of financing these projects or alternative ways. SMRs might be one way. States borrowing the money at much lower interest rates than companies might be another. But if we can overcome the short-term hurdle of the economic viability, I think the sustainability benefits are huge. Thank you very much.